introduction. I hope I'm audible and my screen is visible.
Yes, sir, you are audible and the screen is visible.
Okay, and my slides are changing as well.
Yes, it's
Okay, great. Okay, so thank you very much for inviting me to this wonderful workshop. So today I'm here to talk to you about physics of dynamical horizons and their applications to numerical relativity. And what I'm going to talk to you, what I intend to do today is to give you an introduction to what dynamical horizons are. I believe you have already had a nice exposure in one of the previous sessions. And further, to bring about some recent developments in the field, which is exciting and which I'm currently also contributing to. So let's start the talk. The plan of the talk is as follows. In the first part, I will give a brief overview of isolated and dynamical horizons, with particular emphasis on their applications to numerical relativity. Followed by, in the next section, I will describe one of the most important products from numerical relativity simulations, which are gravitational waveforms, which are crucial for detecting signals of binary black hole coalescences. I will also describe briefly the kind of post-processing that is required to, prepare the gravitational waveforms which are computed through numerical relativity simulations and make it ready to be used in waveform models. Finally, I would like to spend the next half of the talk, hopefully, I'll have that much of time left, in describing some of the recent developments in the field. Okay, onto isolated and dynamical horizons. You might have already heard about these topics, so I'll try to be brief, but please feel free to ask questions if you want me to go slow. Let's imagine a situation. We are now looking at the left-hand side figure. Let's imagine a situation where there is flat Minkowski spacetime. There is no gravitational radiation falling in until a certain instant, which is marked by this line here, wherein a null fluid starts collapsing inwards. And once that happens, of course, it's inevitable that a black hole should form. And after a finite amount of time, suppose the collapse ceases and the space-time becomes stationary or static. What we would expect is that the space-time would have an event horizon, which is described as the boundary of the causal past of future null into infinity, which is exactly this line. So how we would identify this is basically that we wait till all the dynamic ceases, and then we track light rays backwards in time and find out the last light rays that reach from the innermost regions of the space-time to future null infinity, the last light rays which can escape out to future null infinity. And once you start drawing these light rays, you suddenly realize something. What is that? So the very interesting part in this exercise, you realize that the event horizon would actually extend to regions of space-time even before the start of the null fluid collapse, which means you could as well be sitting in a region of space-time which might be engulfed inside a black hole sometime into the future in anticipation of matter or some kind of energy that might fall in. So there might as well be an event horizon that's developing in this room right now. You might have heard this phrase. So this brings up an interesting, troubling aspect of these event horizons, namely that they are teleological in nature. They can form and grow in regions of space-time which can be flat. They can form and grow in response to nothing falling into the space-time. Ideally, we would like to have horizons growing in response to a local flux of energy into the space-time. This is clearly not the case. So right away, we begin to realize that to study dynamical situations, event horizons are probably not useful. There are several other troubling issues about the usual event horizons. Especially suppose we want to study a space-time wherein there is a ring of matter or there is a certain amount of dynamics happening elsewhere away from the black holes, but the black hole itself is not absorbing anything. The black hole itself is static or stationary. Even in that context, the usual way of studying black hole thermodynamics or mechanics is insufficient because of the requirement of global stationarity. We often invoke the presence of a killing vector field, a time-like killing vector field throughout the space-time, and this just seems unnatural because if we are interested in the dynamics of the black hole itself, why do we have to care about what's happening elsewhere? Furthermore, if you look at the first law of black hole thermodynamics, there are quantities like the mass and angular momentum which are defined at infinity, actually. However, the other quantities like the area are defined at the event horizons of black holes. So therefore, you need to go back and forth between two surfaces, and clearly it's not local. Furthermore, there's an ambiguity in the definition of black hole parameters, which means that if there are other objects in the space-time and you want to calculate the mass of the black hole, the ADM formalism cannot be used because intrinsically it will give you the total mass of the space-time. Recently, there has also been research that indicates that event horizons can be non-smooth. They can have creases and they can have corners. Furthermore, it's known that one would require the existence and completeness of future null infinity because of the very definition of the event horizons in order to define it. So, given all these issues, it's wonderful that we have learned so much about black holes using the notion of stationaries in static spacetimes and the notion of event horizons. But once we get into dynamical spacetime, especially since the successful numerical relativity simulations of 2005 and 6, we need to go farther and we need to employ more sophisticated tools to understand the physics of spacetime. So the first idea that I would like to describe today in the context of quasi-local horizons is a non-expanding horizon. And the idea is to basically do away with everything that is global, do away with all aspects of our usual treatment, which refers to things away from the horizon of a black hole, and restrict ourselves to only what's happening at the horizons. And the idea for this originally initiated in Penrose's treatment of the singularity theorem, later on developed by Hayward in the mid 90s, followed by a great systematic development that has happened with regards to Ashtekar, Krishnan, Booth, Fairhurst, and the others. So the first of these ideas is a non-expanding horizon. And the idea is to understand that if you have a horizon which we want to describe as being in equilibrium, then we would want it to be three-dimensional. Cross-sections are space-like, S2 topological spheres. And then there is a null direction, so it's a three-dimensional S2 cross R type of topology. And then we would like to have any of the null normals of this structure delta have a vanishing expansion. What is meant by expansion is basically the fractional change in the area of cross-section of a bundle of light rays that are instantaneously leaving the surface of the horizon. And instantaneously, they can be parallel. Inside this structure delta, you would find that the expansion is negative, meaning that light rays would converge irrespective of what direction you would shine it in, and therefore these regions of space-time are called trapped. So just from these consideration and also certain constraints on uh, the the energy condition of the space-time, one can do quite a lot. One can show that if you have such a structure which does not refer to anything at infinity or the future null infinity, you could show that this means that the horizons have a constant area irrespective of the cross section that you choose. There is a lot more one can do. It so happens that because it's a null topology, it's S2 cross R, the three metric of this surface delta is degenerate. And then, but although it is degenerate, it turns out that by suitably choosing these null normals, one can define a canonical connection, a connection component on delta such that it can be also treated in the framework of a weakly isolated horizon. And weakly isolated horizon is what is very interesting because you could start talking about extension of the laws of black hole mechanics to it. So I would not go into the specifics of weakly isolated and isolated horizons, but what I would like to mention is on adapting these structures, on discussing these quasi-local quantities, one can successfully extend the laws of black hole mechanics to fully dynamical scenarios as process laws. And for example, one can recover the fact that the surface gravity of a weakly isolated horizon is constant. And also, this means that one can also describe space-times which have gravitational radiation arbitrarily close to the horizon, but it's not absorbing it, so it is not growing. So irrespective of what's happening in other regions of space-time, one can now discuss in a robust way what happens at the dynamical horizons, at the uh, isolated horizon. Sorry. One interesting consequence, one interesting feature of these isolated horizons is that you can define two sets of numbers called the multipole moments. These are called the source multipole moments. These are very much like the field multipole moments, which are due to Hansen defined at infinity. So these multipole moments are completely defined on the horizons of black holes, and they quantify the horizon geometry in the strong field regime. They quantify the geometrical state of black holes in the strong field regime without reference to what's happening elsewhere. And in this framework, what basically happens is there is the two Ricci scalar of the cross sections of the horizon, which basically encodes information about the mass multipole moments. You similarly have spin multipole moment information coming from the extrinsic curvature. And all these are integrals computed on the leaves or the foliations of an isolated horizon. And it turns out that these numbers invariantly characterize the horizon geometry. And given these numbers, you can reconstruct the horizon geometry. And uh, as an example, if you put n equal to 0 for the mass multipole moment, you would recover the familiar mass of a black hole. And for the spin multipole moment, you would recover the spin of the black hole. And in general, for a Schwarzschild black hole, you would have all the spin multipole moments vanishing, but you would, of course, have all but the mass multipole moment non-vanishing for a Schwarzschild black hole. The situation would be changed for a Kerr black hole, wherein the spin would be non-zero and and even n values of the mass multipole moment would be non-zero. Okay, so now I would like to move on to dynamical horizons. And I would also mention this briefly. I would point you to references for more details. So the idea is very simple, is to use the same concept of trapping horizons and extend it to dynamical scenarios. We would still want to look at the surface, which is marginally trapped, marginally outer trapped, actually. So you would have the expansion of the outward pointing null normal to be zero, and inside you would like to have the expansion to be negative. And in this framework, if you track the surface, which is marginally trapped, it turns out that there's a robust way to define the mass and the angular momentum. It has no teleological properties. You could extend the laws of black hole mechanics as process laws. Um, of course, this would be very useful to study the evolution of black hole horizons in a situation like a binary black hole merger, which is very interesting. And therefore, in this figure on the left-hand side, if you see what is in this gray shaded region is actually the trap region of a space-time, and the boundary of this trap region, which is separating the blue from the gray region, is a dynamical horizon. This dynamical horizon only starts to grow in response to the local flux of radiation that is falling inwards starting from this time. And once these marginally trapped surfaces form, and then they undergo dynamics, and far into the future, once all dynamics ceases, they would asymptote the event horizon of the spacetime. And at this point, the horizon becomes null, which is shown by the top half of the right-hand figure. And in this region, the event horizon would, of course, be coinciding with the isolated horizon of the black hole. Okay, so another interesting point, a viewpoint to look at is if you look at one of the simplest solutions of two black holes, which, by the way, are the starting points for constructing initial data for binary black hole simulations. These are called a family of Brill-Lindquist initial data. So if you look at this solution, the geometry is as follows. You basically have a sheet, which is a three-dimensional hypersurface, and embedded in them are two punctures wherein the surfaces of these punctures would represent the black holes, each of the two black holes. And it turns out that because of the nature of the coordinates that were chosen to solve to get these punctures, these have their own free asymptotically flat ends at 2 points. And this is a very special case if you solve the constraint equations with a lot of assumptions, namely moment of time symmetry and no linear momentum and so on, you would recover this solution. And what is interesting is that if you compute the area mass of the spacetime on the top sheet, you would get the total mass of the two black holes. But how would you even compute the individual masses of two black holes? If you imagine in a numerical simulation at an instant of time, you would have two black holes. And how would you do that? If not for these two bottom sheets, there was no way of computing the individual masses of the two black holes. It turns out in this case, because of the simplicity of solution, that using the asymptotically flat ends of the individual punctures, you could actually compute the individual contributions to the masses. But however, in a general numerical simulation, if you stop a numerical simulation, take a snapshot, you would get a hypersurface which is three-dimensional, but you would not have access to these regions because of the complicated dynamical gauge conditions. So it seems that there is no way of computing individual contributions of masses. And this is where the concept of dynamical horizons would be very useful. One would find in a numerical simulation the surfaces which have zero expansions. And by computing certain integrals on these surfaces, one can actually compute the individual masses and the spins of the black holes. Okay, so till now we have talked about this region of space-time in the strong field regime, but there's of course the most important region of space-time where our detectors are positioned, which is at future null infinity. And I would now like to shift our focus to this region before moving over to discussing some of the recent results in this field. Okay, so here is a picture of a snapshot of the curvature in a binary black hole merger simulation. This is the XY plane. These are two black holes. And these simulations are carried out using Einstein Toolkit. It's an open source finite difference code. And therefore, you see these several levels of mesh refinement, which are required to resolve the finer features of the space-time in strong field regions. So you would see nested refinement levels. Anyway, so I would give a brief overview of the numerical simulations that I ran in order to understand strong field dynamics of black holes. So numerical simulations are very expensive, as you might have heard. If you use, for example, 128 processors, getting a waveform which is barely usable for modeling could take almost 15 days, and each simulation can eat up around 4 to 10 terabytes of space. And there is a lot of processing that's required before one can use the waveforms, which I will now describe. Um, how we would run numerical simulations is you would first choose parameters of initial data to start with. You need initial data to start evolution for any system. And the initial data would include, for example, the individual masses of the black holes and their momenta. And once these are chosen, there's a way to choose them using post-Newtonian theory. Once these are chosen, then the evolution system will take over, will find initial data first. For example, the elliptic solvers would find the first initial data, and then the evolution system would take over and evolve the space-time. And this figure shows, for example, two black holes which start off at the left extreme and the right extremes. This is the centroid of the two black holes, which start merging on quasi-circular orbits and finally conclude into a final black hole at the center. And this is how distance between the two black holes would decrease in time for different mass ratios. And one of the most important things that we get the products of these numerical simulations are gravitation radiation. which is crucial for detection. And how these are computed are that we use a Newman-Penrose formalism and we project the components of the wild tensor on a suitable choice of null tetrad very far away from the domain of numerical simulation. Why can't we go up to infinity? It turns out that if we use formulations like 3 plus 1, then we, of course, have finite amount of computing resources. So we cannot afford to keep enlarging our domain. At a certain point of time, adding domains, increasing the size of domain would not affect the result so much. It turns out that you can extract waveforms on large enough spheres, which are typically 500 times the distance of 500 times the total mass of the space-time. And that would be sufficient to compute gravitational radiation and extrapolate them by doing perturbative corrections to the waveform. And these corrections are done by basically computing the wild scalar on different spheres of different radii and then using certain favorable properties of the wild scalars. For example, the peeling properties of wild scalar psi4 should decay as 1 by r as r increases. And if you are not exactly at r equal to infinity, you would have contributions like 1 by r squared, 1 by r cubed. And using data from different spheres, one can discern what is the coefficient of 1 by r. So this process is called extrapolation. And after having extrapolated, one should, of course, do other corrections. This is the extrapolation that I spoke about. There is also a perturbative way to extrapolate. You can assume the space-time inside the domain is a perturbed Kerr black hole, and you can try to extrapolating using that method. And that's also favorable. And once you do extrapolation, of course, they introduce certain changes in your waveforms up to a level of 1%. What you see on your screen is the changes in phase due to extrapolation of the waveform. So these can definitely not be neglected. These would lead to biased models if they were not done. Another aspect to worry about is a center of mass drift in simulations. Due to physical and unphysical reflections at the domains, or at the boundaries of the domains, the center of mass of the black holes can drift. And as you can see, the orbits are slowly drifting away to this corner. And these would, of course, introduce certain changes in the modes that were extracted on large spheres because the spheres remain put. They don't move in a numerical simulation. And these spheres are used to decompose the wild scalar into their spin weight -2 modes. And therefore, these would introduce a certain amount of change in the coefficients which have to be corrected for. And these can also be done, and these are related to BMS transformations of waveforms as well. And these also bring in a sub% change in the gravitational phases, which are important. Finally, we would like to integrate out psi4 to get the strain. And it turns out that integration of psi4, which involves two-time integrations, is not actually straightforward. The reason is because numerical simulations are not, of course, 100% exact. They have certain noises, they have certain departures, small departures, of course, acceptable departures. And these departures at low frequency regimes uh, induce a certain wavy feature, wavy artifact in the waveforms if you naively integrate them using any sophisticated RK techniques, for example, in time domain. So what one would do is either use a notion, what is known as fixed frequency integration. And if you use fixed frequency integration, you can get rid of these oscillations, as you can see in the cyan color here. The magenta one is time integrated naively using RK methods. You could also do energy minimization approach. That's the alternative, and one would recover the same result. And what you see in green is directly is a strain directly computed from psi4 using Cauchy characteristic evolution methods. So we can see that the cyan curve is very, very close to the green curve here. So once you do all these things, we are good to go. We have several waveforms from numerical relativity, which are ready to now be used for waveform modeling. I would like to pause here for a couple of minutes and see if anyone has questions before I move on to the last part of the talk.
Hi. So I have a small question. So when you talk about this integration method, that fixed frequency integration,
Mhm.
and why does that give different results compared to the arcade code? I mean, what is so special about this?
So what fixed frequency integration does is basically it identifies low frequency noise in the Fourier transformed version of the strain of Psi4, and then basically sets that to zero. And once you identify, the hard part is identifying exactly what frequencies constitute the unfavorable frequencies. And once you do that, you can do a spectral integration. Basically, you know that this, you know the differential of sine and cosine, so you know their integrals as well. You can integrate them spectrally, and you can obtain the sine curve without the artifacts.
Yeah, thanks.
Sir, I have a question. So, can you once again explain what is meant by teleological nature of horizon and why event horizon is teleological and dynamic horizon is not teleological?
Okay, sure, I can do that. Let me just head back. Okay, so in short, in order to in order to find out the location of event horizon in a space-time, you need to know the entire dynamics of the space-time infinitely into the future. You need to be sure there's no further dynamics happening, and the final dynamics that happens actually defines the location of the usual event horizon. And here you realize that once you draw the event horizon in your space-time, you realize that event horizons can exist even in those regions where there is no dynamics happening. So in this initial orange region, there was no matter or radiation which is falling in. It was just perfectly Minkowski flat space-time. But because of dynamics that happened later on, a black hole formed, and the space-time has an event horizon, and and light rays from this region can therefore not leave this part of the space-time, can never reach future null infinity. So an event horizon exists even in a flat region of space-time. So an event horizon here is appearing because of dynamics that would happen sometime into the future, in anticipation of something that will happen into the future. And this is what is meant by teleological nature of horizon, of event horizons. And dynamical horizons are devoid of this because we have no references to future null infinity in defining them. We are just interested in how how null rays behave. We are tracking the surface, which has a zero expansion, and all definitions are quasi-local. I hope that explains the question.
Yeah, yes. And
Okay.
Hi, Vaishakh. May I ask one small question?
Yes,
Uh,
please.
yeah, so you mentioned about this garage Hansen multiple moments, etc.
Mhm.
So recently there are some attempts to extract near horizon physics from far region, from the horizon multiple moments, etc. So can you, I mean, comment what best we can extract from those multiple moment calculation, which perhaps one can only get at the far region, and
Yeah.
what those can talk about the nature of the black hole, whether it's spinning, how fast, etc.
Yeah, sure. This is definitely an interesting question. We do not currently know how the field multipole moments are related exactly to the source multipole moments, which are multipole moments of dynamical horizons. But hopefully, in this section of the talk, I do have some aspects of this that I would touch on, and hopefully, your question might be answered there. Could we wait for this section of the talk for
Okay,
that?
okay, yeah, sure, sure.
Okay. Okay, so I believe I have how much more time? 20, 25 minutes? 30 minutes?
Yeah, you have
Yeah.
almost
Okay,
30 minutes.
okay, fine. So let's now discuss some of the recent developments in applications of dynamical horizons to numerical relativity. This is very interesting, as I mentioned, because we are now detecting gravity waves from coalescing binary black holes. We have quite a few of them now. And the success of numerical relativity in 2005 and 6 have enabled um, us to start asking questions like, how does the strong field dynamics of a binary black hole system behave? Can we understand these dynamics? We, of course, know a lot about what happens at infinity, but can we really probe what's happening in the strong field region? And therefore, there is interest in understanding dynamical horizons, what's happening at the horizons, and how they may be related to what's happening to infinity. So before the advent or the success of numerical simulations, there were speculations about the possible correlations between what happens near the horizon of a black hole in a perturbed spacetime. Let's imagine a single Kerr or a spot-sheet black hole which is perturbed, and in such a situation, there were hints or there were conjectures or expectations that um, there is some gravitational radiation definitely that's being absorbed at the perturbed horizon. And there's also a part of the field that leaves the space-time and goes to infinity. And it's possible that the nonlinear regions of space-time which generate these waves majorly uh, are responsible for sourcing both the waves that are falling inside and the waves that are escaping to infinity. And they may be correlated. So this was a conjecture. And there are several works, there are a couple of works in literature which conjectured the existence of such a correlation in perturbed scenarios, in, for example, head-on merger situations, and also quite recently in a binary black hole merger scenario. So what you see on the bottom plot is the flux of gravitational radiation that is computed at infinity and the flux which is being absorbed in the post-merger phase of a binary black hole merger. And qualitatively, they seem to look similar. So the interesting question to ask is there a correlation between what's happening at the horizon and what we get at infinity? And this is a big deal. Why? Because if you look at this plot, this is actually a cartoon. Please don't take this very seriously. This is like a Penrose diagram, but not exactly, but it illustrates the point. You have the event horizon forming due to the final black hole, which is asymptoting to equilibrium here. And the progenitor of this final black hole is, of course, a binary black hole merger scenario. You have two black holes, the dynamical horizons are shown here. They are revolving around each other and then slowly contracting and merging here, where a final common horizon is formed, which asymptotes to equilibrium. And the event horizon would basically tell you the region of space-time from which no light can escape to infinity. And you immediately see that dynamical horizons live inside event horizons, so they have no causal connection to what happens at infinity. So the question is very interesting as with regards to correlation, because this region cannot send signals to detectors here. So how do we even probe physics here? And then some of the work that I've been doing in the past few years is to address this question. And what I did during my PhD was to understand not only in the post-merger dynamics, but to understand if there are correlations between physics in the in-spiral phase of binary black hole mergers, in the merger and the ring-down phases, and how do we relate these two, for instance. So the work that I'm going to describe now is mentioned here. Please look at it for more details. So system emits gravitational waves during in spiral. A part of it falls into the horizon, part of it escapes to infinity, but it's all very complicated. You have two black holes in spiraling. And then can we expect correlations in the in spiral as well? The goal is to understand this correlation. And in the dynamical horizon formalism, there is actually an exact expression for the amount of energy that's being absorbed due to gravitational radiation at the dynamical horizons in the strong field regime. This is completely covariant in nature. And one of the major contributions is from the shear of the dynamical horizon. Shear is what it geometrically is, a Newman-Penrose scalar, and it contains certain transverse traceless projection of the derivatives of the null normal. And this has a resemblance to the gravitational energy that's being escaping to infinity, and that involves the integral of the News function. So what I did in this work is to compute the shears at the dynamical horizons of each of the two black holes in the in spiral, and also the common dynamical horizon in the post-merger phase, and then see if they are interesting, first of all, and secondly, if these are correlated in any way to the waveform that we receive at infinity. So here is a result. So what is shown in blue is the News function received at infinity, which is computed from the numerical simulation. And what you see in orange is the shear on one of the two dynamical horizons in the in spiral phase of a binary black hole merger. And as you can see, once you align them suitably by a time shift and a phase shift, they seem to agree excellently. The shear seems to have a familiar chirp-like behavior, which means it has increasing frequency and amplitude, much like the gravitational waveform, and they go they go hand in hand, in fact, all the way up to the merger. There is some deviation in the amplitude fall off, which we associate with the inaccuracies in the computations of the shear. But however, as you can see, the phase is matching very well. And these were done for a handful of binary black hole mergers with different mass ratios. And we showed that one can recover the parameters of the system using not the News or the strain, but actually the shear at the dynamical horizon. And the match between them are quite good. They are above 96%. Furthermore, we also found that one can, in fact, compute in an approximate phenomenological fashion the shear of the two dynamical horizon using just the News of gravitational radiation, which means you can do this without even running a numerical simulation. So these relations are very interesting because this offers one of the first ways to probe the strong field dynamics of black holes in full nonlinear general relativity. It's a surprising relation, and it would possibly allow us to improve, for example, our current waveform models and carry out tests of GR. And now I would like to also explain how this relation plays out in the post-merger phase of binary black hole mergers. And as you may all know from black hole perturbation theory, uh, the perturbation theory says that if you're treating linear perturbations, if you're trying to solve for linear perturbations of a black hole, then you have quasi-normal modes, you have damped sinusoids. But however, in a binary black hole merger situation, as you may have seen in today's talk by Prayush, that once two black holes come very close to each other, a common horizon forms, which is highly distorted. It's very far from what an equilibrium curve black hole looks like. So the dynamics is highly nonlinear. But what we try to understand is it possible to describe the dynamics of this remnant of the common horizon that is formed using quasi-normal modes, which, because it comes from linear perturbation theory, how well does it agree with the theory of quasi-normal modes, and how well does the correlation between the News and the shear continue to hold in the ring down phase. And here is a sample result from such an exercise. What is shown in blue is again the News in the post-merger phase, and what is shown in orange is the shear at the common dynamical horizon. And they have also been suitably time shifted and aligned because the News takes certain time to reach the extraction sphere and the horizon is in the interior. So once you do all that, you see that the phasing of the two agree very well, and the slope of this, the decay pattern, agrees quite well with the dominant quasi-normal mode. What you see on the right-hand side is a numerical noise floor. All numerical simulations have limitations, and on increasing the resolution of the runs, the noise floors would be expected to decrease further and further. And of course, we could find a similar relation between the shear and the News in the post-merger phase as well. Another interesting consequence of this exercise was that you could recover the spin of the final black hole formed using the shear at the dynamical horizon by just carrying out a similar template-based parameter estimation or a best match kind of an exercise and feeding in not the gravitational wave strain at infinity, but the shear at the horizons. You could, in fact, we also showed that you could recover the individual masses of the parent non-spinning binary black holes that led to this common horizon. Okay, so I would again pause here for a couple of minutes before moving on to the last part of my talk. Are there any questions at this stage?
There's a question in the chat actually. I think
Okay, let's see.
Siddharth is asking, are there any other ways to visualize and understand dynamical horizons? I mean, without more technical terms.
Okay, so we can discuss about this. We can discuss about this. I've been working on certain visualizations. Maybe they could help. I will show one of them here. Uh,
Okay.
maybe you could write to me and we can discuss about it.
Okay.
Thanks for the question.
Yeah, there are no other questions right now, so you can go.
Okay, now I would like to move on to another aspect, another problem which I've been trying to investigate in the past few years, which is in connection with tidal deformations of black holes. You all may have heard that non-spinning black holes do not deform. And what we intend to do, what we wanted to do in this line of investigation was to um, is to propose an alternative formalism, an alternative approach to the problem of tidal deformations of black holes using not the gravitational field at infinity, which is what is usually done, but using actually the geometry of the dynamical horizons. And details can be found in this paper. Please feel free to look it up. So the system is same as the previous case. We have a binary black hole system, two black holes. This particular one is asymmetric. It's non-spinning. Mass ratio was about 0.6. And this is a top view. Gravitation radiation is visualized here. You see nice lobes of dominant quadrupolar pattern. And the question is, of course, the two black holes deform. These are non-spinning black holes. So the field approach, the field treatment would imply that they don't deform. But what we want to ask is, do the horizons of the black hole deform? And can we associate any strong field of numbers to the deformability of these black holes if they do deform? And the deformation would happen because of the mutual influence that these two have on each other. So the present treatment of tidal deformation, of course, has taught us a lot. The perturbation theory of black holes has taught us a lot. However, they have their own limitations. They cannot be applied in scenarios like binary black hole mergers when the two black holes are very close to each other. Why? Because when the two black holes are very close to each other, they start moving fast. They could approach up to 60% of the speed of light. They come into mutual strong field regions, which means you can no longer associate an asymptotically flat region to each of the two black holes. In order to do a perturbative study, you need to have access to the asymptotic regions of each black hole. You need to be able to differentiate between the contribution of gravitational field of first black hole and the second black hole to the total field at infinity. Such a treatment becomes impossible when the two black holes close in. There are also uh, discussions currently happening on whether the results on the field tidal of numbers are gauge invariant and so on. So these are interesting investigations that are happening. So we wanted to propose and we wanted to find an alternative approach to understanding tidal deformations, which would be valid even in strong field regions, in highly dynamical regions where you cannot asymptote the asymptotic fields of each black hole. And we want to do this using dynamical horizons. And how we do this is using the source multipole moments. Remember, we talked about source multipole moments. There are two sets of numbers, mass, which is shown here, and spin, which is not shown here. These mass multipole moments characterize the geometry the state of geometry of dynamical horizons. And these integrals are carried out on the leaves or the foliations of dynamical horizon. So this is a three-dimensional dynamical horizon. This is space-like. It has a time-like normal. So it's a one-way membrane. You can only enter it. You cannot leave it. It has a space-like tangent. And then the normal to this space-like tangent is, of course, topological spheres, which would represent instantaneous horizons of black holes in a numerical simulation. So in a numerical simulation, you would have a three-dimensional Cauchy slice, which I have not drawn here. You could imagine that to be a flat sheet. And that would intersect with this three-dimensional tube in a two-sphere, which is labeled by S. And each of these would represent apparent horizons of the black holes, the instantaneous horizons of a black holes. And on these surfaces, if you compute the expansion of the outgoing null vector, they would be zero. And the expansion inside this surface would be negative, meaning that all closed surfaces inside would be trapped. Of course, at late times, you would imagine when there's no dynamics happening, it would asymptote to an isolated horizons where the tangent would be a null vector. So the null vector would be both tangent and normal to the surface. So coming back to the problem of tidal deformations, we would be computing multipole moments on each of these surfaces, leaves S, which represent apparent horizons in a numerical simulations. So we would track the apparent horizon. We would solve a certain elliptic equation at each instant of time in a numerical simulation, find the location of these trapped surfaces, and then compute these multipole moments on each of these trapped surfaces. And why would we do that? We do this because we know what these multipole moments are for an isolated Schwarzschild black hole or a Kerr black hole. Here we are discussing numerical simulations of non-spinning black holes. So it would be apt to compare these numbers with a Schwarzschild black hole. We know what these numbers are for a Schwarzschild black hole. In a numerical simulation, each of the two black holes would be affected by their mutual gravitational interaction, and therefore the geometry of the horizons would change, leading to a change in these multipole moments. And this is the starting point. Using these multipole moments, which are dynamical, by the way, because each Cauchy slice would intersect one such leaf, S, one such apparent horizon. And as time proceeds, we would get different intersections, and they would represent dynamical state of the horizon at each point. So therefore, these multipole moments would also evolve with time. And then uh, by comparing these multipole moments to what an isolated Schwarzschild black hole would have, we can quantify the deformations of the horizon. And these deformations, we showed that can be expanded in simple in a simple expansion, much like a Taylor expansion involving the parameters of the binary black hole system. Here, MTD and MTF are the masses of the individual black holes in the in-spiral phase, tidally deformed, and the one that is sourcing the tidal field. So this expansion can be carried out for each of the two black holes. There are two different dynamical prices, and D is the distance of separation between them. Since these are the only parameters in the system, you would expect the coefficients which are accompanying them to be dimensionless and scaled out. And by running numerical simulations, tracking apparent horizons, computing these multipoles, and calculating these numbers, we aim to quantify the tidal deformability of black holes. And these could be called as strong field love numbers. So here is a plot of how this model that you see on the screen can be successfully used to explain how black holes deform. So what you see on the screen is the n equal to 2, the quadrupolar deformations of black holes, of one of the two black holes, black hole 1 actually, the one which is more massive, that's plotted on the y-axis. And what's plotted on the x-axis is the distance of separation between the two black holes. The data points in black are computed from numerical data, from numerical relativity. And what is shown in cyan and magenta are two different models, each one involving one particular term in this expansion. The cyan model actually involves a leading order expansion, the expansion goes from 1 to infinity. It's an expansion in 1 by d. So if you think about it, the reading order contribution should be 1 by d cubed because of the tidal fields. And the higher order would be 1 by d power 4. So the cyan model actually stops at 1 by d cubed, but the magenta one also includes 1 by d power 4. So model 1 by d power 4, as you might imagine, would be more useful to explain the behavior of multiple moments, especially when the black holes are close to each other. So simulation would start from here, where the distance of separation is maximum. As the black holes come closer and closer, distance of separation would decrease. So black holes, the quadrupolar deformations of black holes increase as the two black holes coalesce. And these are non-spinning black holes. So this shows that even non-spinning black holes deform. And we could successfully compute these tidal coefficients. The first few tidal coefficients are shown here, and these could be called as a strong field of numbers of black holes. Okay, so given that these deformations were found and that these deformations are interesting, what I attempted to understand was, of course, the connection between these deformations and what happens at infinity. Because immediately when we realize that non-spinning black holes also deform, the next important question to ask would be, would it really affect what we see in our signals? Because we currently assume tidal deformability to be 0. And this work attempts to address this question. It's a very difficult question. So there is some progress, and I would like to briefly mention that. So, so one realization, of course, that came about was that we should be not restricting ourselves to a single index or axisymmetric deformations of dynamical horizons, because as you can see in this figure, there is nothing axisymmetric about this situation. You have two black holes, and the situation is highly non-axisymmetric. You would imagine deformations to have all possible components. So immediately, what I did was to compute certain generalized multiple moments. These multiple moments are defined again on the dynamical horizon, but using a more general basis function adapted to the deformed horizon geometry. The Ricci scalar of the individual slices, leaves of the dynamical horizon are expanded, projected on these bases, and these generalized multiple moments were computed. And as I mentioned earlier, M00 would be the mass. We now have two indices instead of one. And for a Kerr black hole, for instance, M20 would give you something proportional to a square, which is the spin of the black hole. And you could also equivalently define the spin multipoles with two indices. And J10 would give you the spin. And these would capture the most general deformations that a dynamical horizon could have. And on running numerical simulations and computing these general deformations, what I found was on your screen, the dominant contribution, what we were looking at before in the previous part of the talk was the L2 M0 component. Remember, we didn't have the M in indices. It is still a quadrupolar deformation, but it is an axisymmetric component of the quadrupolar deformation. It turns out there are a host of other contributions, and the dominant one is actually L2 M2, which is shown here. And these are oscillatory in nature because they are complex. And as you may imagine, with time, their strength increases as the two black holes come closer and closer to merge. There are different contributions to deformations of dynamical horizons, and they all increase in strength with time. And some of them remain zero, of course, because of symmetry consideration. If you have a non-spinning system and you have the system remaining on the equatorial plane, then there's a reflection symmetry with plus z and minus z. Numerical simulations don't assume any symmetry. So therefore, you have certain noise instead of any data, and certain multiple moments would be zero. And here is a visualization of the deformed state of dynamical horizons in the due process of a merger. And I would like to show you a short video. I suppose I'll have to stop sharing and resume a different screen. Let me try that. Can you see the video in the background?
Yes,
Yes,
sir.
yeah.
Okay. So these are these are the apparent horizons of the black holes, which are basically cross sections of a dynamical horizon. And what is plotted on them are the components of the two-dimensional Ricci scalars, which inform us about their tidal deformative state. And I will now play the animation. And as you can see, and I'm going to pause him here. So as you can see, the region which is red is actually along the line joining the two black holes. And therefore, this tells us that hole one induces most deformation, which is facing it. And this pattern actually follows the evolution or the binary, the orbital evolution of the system. The gravitational waveform from the system is plotted below. And as time goes on, the deformations increase due to the intensity of the colors, as you can see here, before they would finally merge to form a single horizon. Okay, going back to the presentation. What you see on the screen is a snapshot from the same movie. So the two black holes deform each other, and you can clearly see the L2 M2 dominant quadrupolar pattern. And now coming to correlations, it was interestingly found that these deformations, which are plotted in cyan, the dominant component, are also strongly correlated with the news of gravitation radiation, which is escaping to infinity. And this is very interesting again because the dynamical horizons are causally disconnected from observations. We now know that dynamical horizons deform. So if there is any hope of understanding how our waveform models could benefit from this could be a first step. This shows that these are correlated and there is a strong reason to pursue the effect of these deformations on the observed gravitational waveforms. And interestingly, there were some other results that were found, namely that the qualitative details of the dynamics of the binary black hole system are imprinted on the horizons of the black holes. What is shown in red line is basically the innermost stable circular orbit, the approximate location of it, computed from resummed Hamiltonian. And what you see plotted here are the multipole moments very close to that location and very close in the neighborhood of this location of ISCO, you would see that there is a sharp change in the growth rate of these multipole moments. And some of the deformations, which were very small, also pick up. So black holes seem to gain hair as binary black hole merger proceeds. They gain more and more deformations. And finally, you could also compute them on the common horizons of the two black holes, and it was found that there is a quasi-normal behavior in how the multipole moments or the deformative state of the common horizon decays with time. And therefore, whatever gravitational hairs that the system gained in the in-spiral phase are actually lost in the post-merger phase, because in the beginning, we start off with if you start off with two black holes which are infinitely separated, they would be non-deformed. They are symmetric. And then finally, you have a final curve black hole, which is also not deformed. In between, there's a lot of gravitational hair that it gains. And in the end, in the common horizon, those gravitational hairs are lost by absorbing gravitational radiation. Dynamical horizons absorb gravitational radiation, losing their hairs. So this leads to an interesting refinement of the hypothesis or the conjecture that there are correlations between strong field and the weak field regimes. Possibly the full multipolar structure of the dynamical horizons could be correlated with that of the Bondi flux at future null infinity. Uh, I would also like to mention some other interesting results, which possibly will be talked about in tomorrow's session. For example, quasi-normal behavior in head-on collisions have also been found with overtones, and also certain nonlinearities in head-on collisions have also been found at the horizons quite recently. This so there are a lot of interesting physics that one could extract using dynamical horizons. I will now come to the summary of my talk. Black holes are certainly one of the most interesting and important sources of gravitational waves. Recent progress in numerical relativity has enabled us to start probing the strong field dynamics to understand how black holes really evolve, and dynamical horizons are very useful for that. Quasi-local horizons and with quasi-local horizons and numerical relativity, one would be equipped to study the dynamics in the strong field regimes of black holes. Recent developments have shown that the strong field dynamics is strongly correlated with the weak field dynamics in all three phases of a binary black hole merger. So we could think of probing the strong field dynamics and possibly doing tests of GR. And importantly, non-spinning black holes also tidally deform, and gravitational waves from such systems can carry their imprint. These deformations can be predicted using phenomenological relations. So the multipole moments could be computed using the news because of the correlations using certain phenomenological relations we have. Finally, there is also evidence of quasi-normal structure at the dynamical horizons, even though they may be in a highly deformed state where we would not normally think of applying uh, linear perturbation theory. And there have also been evidences of non-linearities that have been found. So I'll stop here. Thank you.
Thank you very much, sir, for such a nice talk. And I ask the participant, please ask if you have any question. Shiji, sir, you are there. You may please.